Yesterday, you learned a little bit about the photoelectric effect, which says when light strikes a piece of metal, an electron is sometimes ejected, not all the time, but sometimes. Hertz argued in 1887 and in the years following that, that if electrons were being ejected, it was because the light that struck the metal had sufficient energy to cause the electrons to be ejected. He also reasoned that if electrons weren't being ejected, we needed more energy in the light to cause the electrons to be ejected. And that part of his argument, that part of his explanation was correct. But where he got the energy from was not correct. Hertz reasoned that we need more energy, and we're going to get that more energy from either brighter light, more light, brighter light, or shining the light on the metal object for more time. In either case, we're going to get more light, which means we're going to get more energy. But that didn't work. Okay, that didn't agree with the observations that were made for 18 years using the photoelectric effect. Nobody could explain why, if light didn't cause electrons to be ejected, why shining more light or light for a longer period of time on the metal didn't cause the electrons to be ejected. Nobody could figure that out, but they didn't. At the same time, people noticed that if we used a different kind of light, then it would cause the electrons to be ejected, but nobody knew why. Until Einstein in 1905, who said, light is a particle called a photon, a quantum of energy. Light's a particle. And each particle of light has an energy that's equal to the Planck's constant times the frequency, or Planck's constant times c over lambda. Einstein said that the energy of the light is not related to the intensity, or it's not related to how long you shine the light on the metal for, or it's not related to, in general, how much light you have, but rather it's related to the type of light. Higher frequency, higher energy. And that agreed with the observations that were made. For 18 years, people had noticed that I changed the kind of light, the type, the frequency, and I'm causing electrons to be ejected, but nobody knew why. Now we know why. In 1905, when Einstein said that the energy is related to the frequency, this told us why increasing the frequency would cause the electrons to be ejected, because it also increases the energy. All right, a couple terms here we talked about yesterday as well. The threshold frequency is the minimum EMR frequency, the minimum frequency of the light that's necessary to eject an electron. If your light is below the threshold frequency, and we saw this with our demonstration, right, when we had one photon striking the piece of metal, then nothing's going to happen. If it's above the threshold frequency, then one photon will cause one electron, or 20 photons will cause 20 electrons, or 1,000 photons will cause 1,000 electrons, but only if you're above the threshold frequency, the minimum frequency of the light necessary to eject the electron. Bless you. The work function is the minimum electromagnetic radiation energy necessary to eject the electron. If the photon is above that energy, then it's going to cause an electron to be ejected. It's a 1-to-1 ratio. One photon, one electron, 5 photons, 5 electrons. But if it's below that minimum energy, the work function, then nothing's going to happen. No matter what, no matter how many of them we have. We had 20 photons that were below the threshold frequency in our demonstration. Nothing happened. We could have had 1,000. Nothing would have happened unless you're above the threshold frequency, above the work function. Now, we know that E is equal to HF, which is equal to HC over lambda. And because energy is equal to HF, then the minimum energy would be equal to H times the minimum frequency, which, by the way, would be equal to HC over lambda maximum. Talking about threshold frequency, the minimum frequency, threshold wavelength is the maximum wavelength. It's because wavelength and frequency are inversely related to each other. As frequency goes up, wavelength goes down. You need to be above the threshold frequency. You need to be below the threshold wavelength to cause an electron to be ejected. We talked about a couple more terms yesterday as well. The stopping potential. The photoelectric effect has already taken place. We've already ejected an electron. Maybe we want to stop that electron for some odd reason. The electron's been ejected, we want to stop it dead in its tracks. Maybe we want to use the data that we collect when we stop that electron to find the threshold frequency of a metal. Maybe in our demonstration, our piece of metal, our metal object, was some material, some unknown material that we were trying to test to find the threshold frequency for, to see if it would be viable to use in a solar cell. Whatever, we want to find the threshold frequency. Maybe we want to find Planck's constant experimentally. Okay, one way that we can solve for variables relating to the photoelectric effect is to stop the electrons once they've been ejected, once the photoelectric effect has already taken place. Now, once the electron has been ejected, it has kinetic energy. But if we're stopping it with a potential difference, then that kinetic energy will be converted to potential energy. It's like the car going up the hill, if you remember from our electricity unit. Kinetic energy converted to potential energy. 1 FmV squared equals QV stop. Well, both of those end up being equal to the kinetic energy of the electron. We actually talk about it as the maximum kinetic energy and the maximum speed, because the reality is we don't actually know what the kinetic energy of the electron is going to be when it's ejected. We know the biggest that it can possibly be, the maximum value that it can be. Yeah. So when we solve this, any of these variables, it's maximum. 1 FmV squared equals QV stop. And then finally, using the law of conservation of energy, which we kind of already did for this, right? That's conservation of energy. Using the law of conservation of energy in another way, analyzing the interaction itself, photon strikes metal, electrons ejected, we would say the energy that we start with is equal to light energy, photon energy. The energy that we end with is equal to the kinetic energy of the electron that's been ejected. Plus, whatever we used up in the process of ejecting the electron, the work function. Now, unfortunately, this one isn't on your data sheet. This one we have to either derive or remember. The bad news is, this is the one that we use probably the most often. Probably out of every 10 questions involving photoelectric effect, you use this equation 6 times. The reason it's so versatile, the reason we use it so often is because HF can turn into HC over lambda. EK max can turn into 1F mv squared or QV stop. W, if necessary, can turn into HF0 or HC over lambda max. We can see a ton of different forms of this equation by substituting in different smaller equations. It becomes a pretty versatile method for solving a problem. Two final things before we do an example here. Number one, the units that we have to use for this. We've been measuring energy in joules and electron volts the last couple of days. We can still use joules and electron volts almost whenever we want. But if you end up introducing either of these two equations, we must use joules. So up here, got to use joules because we're using those two equations. Down here, if we're saying HF is EK plus W, electron volts is fine. HC over lambda equals EK plus W. Electron volts is fine. But as soon as you replace EK max with either of these, we must use joules. And the second thing, speaking of kinetic energy, is we talked about the electron that was ejected by the photon, this photon. But when we were going through our notes here, we didn't talk about the electron that was ejected by this photon. If we're above the threshold frequency, it's always a 1-to-1 ratio. 1 photon, 1 electron, 5 photons, 5 electrons. But if we're way above the threshold frequency, then what we end up getting is a more energetic electron that's ejected. So 5 photons would cause 5 more energetic electrons, 5 faster moving electrons. 1,000 photons would cause 1,000 faster moving electrons, more energetic electrons. Let's have a look at an example on page 716 here. It says blue light shines on the metal surface shown in figure 14.13. This isn't the example that I want, actually. Sorry, it is. And it causes the emission of photoelectrons. Photoelectrons are electrons that have been ejected from a piece of metal. If a stopping potential of 2.6 volts is required to completely prevent the electrons from reaching the collector, what's the maximum kinetic energy of the electrons? So in other words here, this isn't really, not strictly speaking, a photoelectric effect problem because the electron has already been ejected. This is a problem where we're trying to stop an electron, which we could have done back in Unit 2, our electricity unit. This is like a car going up a hill. Okay, a charged particle slowing down. When that happens, we're going to set the initial energy, which in this case is kinetic energy, equal to the final energy, which in this case is potential energy. If you're talking about a car going up a hill, then we would be talking about gravitational potential versus electric potential. Now we want to actually find the kinetic energy, not V. So why don't we actually replace 1/2 mv squared with just EK max. EK max is equal to QV stop, and that equation is on your data sheet. Although we don't really need it, we can figure it out. It's still on your data sheet. All right, the charge of the electron. Why are we using this value, the charge of the electron? Doesn't say anything. It does actually. It says preventing electrons from reaching the collector. It's always electrons in the photoelectric effect, right? Whenever we need a charge, it's always this. We're trying to find kinetic energy from the stopping potential. We're going to say 1.6 times 10 to the minus 19 times 2.6 volts. This gives us 4.16, 4.2 times 10 to the minus 19 joules. So these electrons that have been ejected have this much kinetic energy, or at least a maximum kinetic energy of that value, given that it takes 2.6 volts to stop those electrons. Why? Like, what's the purpose of that? Again, if you're trying to find the threshold frequency so that you can maybe use that metal for a solar cell to generate electricity, or maybe you want to find experimentally the value of Planck's constant, it would be useful to know the kinetic energy of the electrons that have been ejected. And we'll show you some more detail on what an experiment like that would look like tomorrow. All right. We're going to work on the three questions that go along with that on page 716, please, before we do another example here. All right, let's have a look at question number 2 here, which says convert 5.3 times 10 to the minus 19 joules to electron volts. Remember that on your data sheet, on the left-hand side of your data sheet, it says 1 electron volt is equal to 1.6 times 10 to the minus 19 joules. So we're going to set that up as a fraction. And then we're going to set it up as a ratio. 1 over 1.6 is the same as x over 5.3 times 10 to the minus 19 joules. So what we're going to do here now is take this number up here, basically cross multiply, right? Take this number up here, and we get x equal to 5.3 times 10 to the minus 19 over 1.6 times 10 to the minus 19. Now, somebody this morning was asking me that, like, I'm doing that. I'm getting the wrong answer. Every time I do this, I get the wrong answer. I get something times 10 to the minus 38. Anybody else getting 10 to the minus 38? Make sure when you're calculating this that you do not say 5.3 times 10 to the negative 19 divided by 1.6 times 10 to the negative 19. Because when you do that, you get 3.31 times 10 to the minus 38. What your calculator assumes when you enter it that way is that you're dividing 5.3 times 10 to the negative 19 by 1.6 and then multiplying the whole thing by 10 to the minus 19. What you need to do is enter it like this. 5.3 second function EE negative 19 divided by 1.6 second function EE negative 19. That ties the exponent to the base. And when you press enter there, you end up getting 3.3125. And there we go. Does that make sense, guys? All right. I'm going to do one more example right now. I'm going to skip past a few questions on page 718, which I'm going to ask you to do for homework. I think you'll be able to do them without my help. We're going to skip to example 14.6 on page 719, where it says, using table 4.1, which shows us a bunch of different work functions, energies necessary to eject electrons. We want to find the maximum speed of the electrons emitted from an aluminum surface if the surface has this wavelength of light shining on it. It's a photoelectric effect question. We're ejecting electrons from a metal because of photons. Photons cause electrons. And you might remember that I said if you can't think of which equation to use fairly soon, fairly quickly, go with the one that doesn't appear on our data sheet. Go with this one. HF is equal to EK max plus the work function. Go with that one automatically if you can't think of which one should apply within the first 5 or 10 seconds. On table 14.1, it gives us the work function of aluminum. I've got not the frequency of the light, but the wavelength. So I'm going to replace HF with HC over lambda. I don't have the kinetic energy. I don't want to find the kinetic energy. I want to find the speed. So I'm going to replace EK with 1 FMV squared. And I have the work function. So this conservation of energy equation has changed into HC equals 1, HC over lambda equals 1 half MV squared plus the work function. Now, what value of Planck's constant do you want to use for this one? 6.63 joule seconds or 4.14 electron volt seconds? Why? I've got electron volts for work function. Wouldn't it be more convenient for me to use electron volts to this question? Good. Okay, if I didn't have to put this in here, if I just left it as EK, then I could use whatever I want. And electron volts might be convenient there. But since I'm introducing 1 FMV squared, I've got to use joules. 6.63 times 10 to the minus 34 joules seconds times 3 times 10 to the 8 divided by lambda, which is 125 then times 10 to the minus 9, right? Not 1.25, but 125 times 10 to the minus 9 equals 1/2 of the mass of an electron times V squared plus the work function. But we have to find the work function in joules. So let's convert that. 1 electron volt over 1.6 times 10 to the minus 19 joules equals 4.08 electron volts over X joules. Cross multiply. And when we do, we get 6.528 times 10 to the minus 19 joules. Well, now we just got to solve. Let's go through this on our calculator here. 6.63 times 10 to the minus 34 times 3 times 10 to the 8 divided by 125 EE, right? -9. Let's subtract from that 6.528. Let's multiply that by 2, get rid of the half, and let's divide that by 9.11. And then let's square root that. And the speed of my electron is 1.44 times 10 to the 6. (1.44 times 10 to the 6 meters per second). Good. All right. I think all of you finished up the questions that you were working on before. Your homework is the questions that I was just telling you about, page 718, questions 1 and 2. In addition to that, we've got 719, questions 1 to 3.